Bismillahirrahmanirrahim. Assalamu alaikum, dear student. My name is Dr. Muhammad Adnan Asgar, and today the topic of our discussion is molecular point groups under the subject of symmetry and magnetochemistry. Dear student, so far we have discussed and learned the many things about molecular symmetry, in which we have interpret the different molecules, and we learn how to find different symmetry elements as well as operation in the particular molecule. Moreover, we have also discussed how to construct a multiplication table, and last lecture we have also learned something about the point groups. And today I am going to discuss some more details of point groups. In last lectures we have discussed some of the important points about the molecular point group, and we also discussed a chart diagram for the determination of molecular point groups. While we have also discussed the Schoenflies classification system to find out the different point groups of molecules, we also discussed the non-rotational groups, which is the low symmetry molecules, and single axis rotational groups, and the third one was the dihedral groups, while the last one is the cubic groups. So far we have discussed all the four types of point groups in very detail, and we have now we will learn how we can apply to different molecules, and how we can predict the molecular point groups of different molecules in a quite comprehensive and easy way. The conscious student of chemistry might have noticed that some portion of multiplication tables for ammonia and triphenylphosphine and BH3 have common features. For example, the first nine entries in upper left hand corner of each of these multiplication tables are identical. You are advised to look back the multiplication table of ammonia and triphenylphosphine, and you are advised to construct the multiplication table of BH3. And after the construction of the multiplication table of these three molecules, you will able to learn that the first three entries in the upper left hand corner of each of these multiplication tables are identical. From this observation alone, it is quite obvious that these symmetry groups are somehow related to each other. In fact, the point group for triphenylphosphine C3 is actually the subgroup of both C3V point group of NH3 and D3H point group of BH3. I will show you in the next slides how to find the point groups of these molecules in more details. The symmetry operation in a subgroup meet all the mathematical criteria to form a smaller group on their own accord. Thus, the order of a subgroup must be an integral divisor for the order of the larger group from which it is derived. In order to generate the C3V point group from C3 point group, a mirror plane must be introduced. Without having mirror plane, we are unable to generate C3V point group instead of C3 point group because the rotational symmetry of C3 group, once one mirror plane is introduced, a set of three mirror planes is required. This is the case that we have already discussed in ammonia molecule in details. We have tried to find the complete set of symmetry elements as well as symmetry operations in ammonia, and then we also construct a multiplication table of ammonia. If you are very well familiar with the last lectures and you have learned from the last lectures, then it is quite easy to learn the some important and the advanced techniques and the advanced words about the said molecules. So because of the rotational symmetry of C3 group, once one mirror plane is introduced, a set of three mirror planes is required. In order to generate D3H point group from C3, a horizontal mirror plane must be introduced. The presence of mirror plane implies that there will also be NC2 axis perpendicular to the principal axis, and an improper rotation SN axis should be collinear with the principal axis. For certain molecules, for certain molecules and for certain mathematical applications of molecular point groups having high symmetry, the appropriate subgroup is often used to simplify the number of calculations involved. In this table, it is actually the list of the molecular point groups of the common molecular geometries which would be derived from Vesper theory, and we have discussed the Vesper theories in detail in our previous classes. Only those molecules that belong to a particular set of point groups will have a dipole moment. For example, if I would like to explain more about the table of this molecular geometries, then it is quite obvious that if the molecular formula is AX2 and the geometry is linear, then the possible point group is D infinity H, while in case of trigonal planar, which is the AX3 molecular formula, the molecular point group should be D3H, and all types of molecules that belong to this kind of molecular formula with trigonal planar geometry would have opportunity to possess T3H point group. While in case of bent molecule, if the molecular formula is AX2E, E means there is a lone pair or bond pair. There is a lone pair on that central molecule. So it is also believed that this is if we are talking about X3, X2, X4, X5, X6, so on, it means that all the ligands are composed of identical atom. It is supposed that all the ligands which are attached to the central atom, which is A, central atom is A, and the ligands are represented with X. So it is believed that all the ligands are identical atoms. So if the molecule is bent geometry, have bent geometry, and the molecular formula possesses AX2 and E, then this is the C2V. If the molecular have tetrahedral geometry, and then the molecular point group should be TD, while in case of trigonal pyramidal the molecular formula would be like AX3 and E, which the molecular point group should be C3V. While in case of bent geometry but with molecular formula AX2E2, then there is a possibility of C2V again point group, because we have already discussed a bent molecular geometry with AX2E. So if there are one lone pair or two lone pair, the point group would be same, C2V. The geometry, molecular geometry, if the molecular geometry is trigonal bipyramidal AX3, then it would be D3H. And we have already discussed the trigonal bipyramidal geometry in the form of PCl5 in details. If the geometry is seesaw and the molecular formula would be AX4E, then it would be C2V. If the molecular geometry is T-shaped, then C2V. If the molecular geometry is linear with this formula AX2E3, then it's again D infinity H, that we have already discussed in linear geometry with molecular formula AX2. If the geometry is octahedral with molecular formula AX6, it means one is A is the central atom, X are the same ligands. If it is, for example, A is a sulfur, X is F fluorine, SF6, then the molecular point group should be OH. If the geometry is square pyramidal, the molecular formula may be AX5 E, and the geometry molecular point group should be C4V. While in case of square planar, the molecular formula would be AX4E2, and the molecular point group should be D4H. And I do believe that I have discussed many of the examples related to this table in previous lectures, and we have discussed the even the geometries, even the molecular formulas, and the molecular symmetry elements as well as their possible symmetry operations. If we people are very well aware with these notations that were already used, then it would be quite easy to learn as well as to describe the molecular point group of particular molecules. In order for a molecule to have a dipole moment, the sum of the individual bond dipoles must be non-zero. Thus, any molecule containing an inversion center cannot have a non-zero dipole moment. Likewise, any molecule with more than one rotational axis cannot be polar, because the dipole moment must lie along a single axis of the molecule. So it would be quite clear, and we should have to think about that statement that I discussed. I would like to repeat the statement because it's very important. Any molecule one with more than one rotational axis cannot be polar, because the dipole moments must lie along a single axis of molecule. This restriction rules out any of the dihedral or cubic point groups. Lastly, any molecule having a horizontal mirror plane cannot be polar, because the magnitude of the individual bond dipoles will be equal to the opposite sides of the plane. Therefore, only C1, CS, CN and CNV point groups are polar. The symmetry of a molecule also places restriction on whether or not it is possible for molecule to be optically active. Optically active means chiral molecules can exist in one of the two different isomeric forms which are known as enantiomers, each of which rotates plane polarized light in a specific direction. And you people have very good idea of enantiomers and their possible properties. We have learned many things about the enantiomers and their properties in previous lectures. In order for a molecule to be optically active, its optical isomer must consist of non-superimposable mirror images. This will occur if the molecule has no other symmetry besides the identity element or a proper rotation. Hence, as a result, any molecule having an improper rotational axis, which is Sn, cannot be optically active. This includes the non-genuine improper rotation and S2 inversion operations. Thus, only molecules having point groups C1, Cn, Dn, T, O, and I can be optically active. So a, we should have to be a clear picture in our mind that how different molecules can behave differently with the interaction with light. Either they are optically active or non-active. So for based on this knowledge, I would like to give a problem to you people to think about whether which of the following molecules are polar, and moreover you have to provide the point groups of these molecules. For example, the first one is PF5 and the second is COE and thrice 3 plus, and the third one C is cis dichloroethane, and the fourth one is a cyclohexane in boat form. So we should have to draw the different molecular point groups of these molecules along with their polarity or non-polarity behavior. I do believe that you people now can tell the all the possible questions about the said molecules. For example, first of all, we should have to talk about the PF5, phosphorus pentachloride. Its geometry is like trigonal bipyramidal, and there are so many rotations, like there is C3, there are different C2 and sigma H, sigma V, and different, but there is no inversion. So the point group would be like D3H. How we can see, because the principal axis of rotation is C3, so there is a C2 rotation perpendicular to the C3, so it means that we should have to write the D for the that molecule. So if we have to write the D for this molecule, D, which D, the principal axis rotation is C3 rotation, so D3, we need to write D3. Now Let's talk about the sigmas. There are two type of sigma, sigma H and sigma V. But if there is sigma H in the molecule, we better to go for the sigma H. So we can write that this is molecular point group for PF5 is D3H, and it is non-polar in nature. While uh, in second molecule this is also non-polar in nature, but there is point group D3, only D3, because there is only the rotations C3 as well as C2, but there is no sigma in this molecule. So what about the C, cis dichloroethane? Cis dichloroethane have same symmetry elements like that of water. For example, it have identity, it have C2, it have sigma V and sigma V dash. So there is no other axis of rotation, so only one axis of rotation, which is C2. So we better to write C2 first, then the type of sigma should be there in point group. The only one type of sigma is present, which is V. There is no sigma H. So the point group for cis dichloroethane is C2V. For the fourth molecule, which is the board form of cyclohexane, we have already discussed the cyclohexane in chair form in detail, while we also discussed the board form of cyclohexane in detail. So we have a quite clear picture of cyclohexane in board form in our mind. So, what were the, do you remember the different possible symmetry operations that were present in cyclohexane? Try to remember, try to draw. Yes, it is, there is identity, there is C2, sigma V and sigma V dash is present in the cyclohexane in board form. So if there is principal axis is C2 rotation and there is no other rotation is found which is perpendicular to the C2, then we should have to write C2. While in case of sigma, there is no sigma horizontal is present in both form of cyclohexane. So it is the point group for the cyclohexane board form is C2V, and it is polar in nature. So this is the result of this uh, problem, and we can say this is the solution of this problem, which is the PF5 is non-polar and its geometry is trigonal bipyramidal with T3H point group, while this molecule is non-polar with D3 point group, while the C molecule is polar in nature with C2V point group, while the board form of cyclohexane is polar in nature and possesses C2V point group. So let us talk about another example, and this is your assignment. Determine the molecular point group of Schoenflies notation for each of the following molecules. I do believe that you people are very well familiar with the point groups, and this is your assignment to draw the molecular point groups for water, triphenylphosphine, and BH3. We have already discussed these two molecules in details, and we have drawn the different molecular operations, symmetry operations, as well as their multiplication table. So it would be quite easy for you people to find out the point groups of these molecules. Thank you very much. This